They are in listen-only mode.
Hello everyone, my name is John DeBella, Vice President of Marketing and Sales, and on behalf of Simulations Plus, I welcome you to today's webinar, which will focus on the new features and capabilities in ADMET Predictor 7.0. Michael Lawless, Team Leader for Cheminformatics Studies, will be presenting today. Joining Michael and myself are Anu Sharma, Senior Marketing and Sales Manager, Bob Clark, Director of Life Sciences, and Robert Franchkovich, Team Leader, ADMET Cheminformatics. An opportunity to ask questions will follow Michael's presentation today. You may either send your question using the questions pane on your control panel, or you may ask your question directly using the hand-raising icon. If you're using a telephone to listen to the call, please be sure to enter the unique audio pin displayed when you join the call. When you enter your audio pin, this enables us to unmute your line so that you can be heard. This webinar is being recorded for playback at our website, www.simulations-plus.com. What I'll do is now spend the next 5 minutes just providing you with a very brief introduction to our company Simulations Plus and the various product offerings before we switch things over to Michael's presentation. As an introduction to the company, we were founded in 1996, so we're going on our 18-year anniversary this year in 2014. We are located in Southern California, about 60 miles northeast of Los Angeles, and we are publicly traded on the NASDAQ Stock Exchange with the ticker symbol SLP. We have approximately 30 employees, most of those holding advanced degrees, either PhDs, master's degrees in engineering, or MBAs. And our focus is on the modeling and simulation aspects as it relates to pharmaceutical and biotechnology research. So we offer a variety of programs really assisting from the point at which you start sketching molecules to late-stage clinical development. Now these product offerings are displayed here on the right side of this slide. And what I'll do next is just briefly introduce where each of these products fit in. We offer several products which are going to be aimed at chemists, whether computational chemists, medicinal chemists, and these products are going to be the MedChem Studio and MedChem Designer programs, where you can begin to screen high-throughput screening data generated from compound libraries, begin to classify compounds based upon structural similarity, perform R-table analysis, R-table decompositions, and also use the program to assist with de novo design activities for new compound libraries. Now there's quite a bit of synergy between the MedChem Studio software and MedChem Designer program with ADMET Predictor, which is what we're going to be talking about today. The ADMET Predictor software allows you to estimate a variety of different physicochemical, metabolic, and toxicological endpoints from chemical structure. And you also have the opportunity to take whatever endpoint data you might have captured in-house in order to create your own set of models. So you can utilize ADMET Predictor to assist with screening activities and to also help fill in the gaps with the in vitro data that's being collected very early on in discovery. Now as we start to transition into preclinical development, we start focusing on some of our simulation software tools. GastroPlus is going to simulate the in vivo environment, allowing you to predict dissolution, absorption, pharmacokinetics, and pharmacodynamics for different drugs or different compounds in a variety of different species. As we transition further into the clinical stage, we can use GastroPlus to help us with population predictions, with building PK/PD models, with performing drug-drug interaction simulations, and we can also start working with another program that we offer called DDD+, which is going to be simulating the in vitro dissolution experiment. So this program is going to be aimed at formulation scientists or analytical scientists looking to help with the design of formulations or with the development of dissolution methods for the purposes of IV-IVC generation. The next few slides just provide very brief descriptions of the programs. I've already done this already for GastroPlus, for ADMET Predictor, MedChem Studio, MedChem Designer, and for DDD Plus. And so now what I'll do is switch the presentation or hand it off to Michael so that he can provide you with some details about the new features and capabilities in ADMET Predictor 7.0, which we're quite excited about. Michael?
Thank you, John. Okay, so let me get this organized. All right. Well, welcome to our webinar on what's new in ADMET Predictor 7.0. And so there are a lot of new features in various areas of ADMET Predictor 7.0. And just as an overall outline, first I'll discuss predictive models, then some of the new descriptors that were incorporated into ADMET Predictor 7.0. Talk about new features in the user interface. We also have some new command line interface options that I'll discuss, and then finally discuss changes in ADMET Modeler. So these next few slides are simply kind of an outline of the talk, and then I'll get into specifics on further on into the talk. Okay, so first of all, ADMET Predictor has roughly 140 predictive models. All of these models were retrained for ADMET Predictor 7.0, and this was quite a bit of work on our staff's part here. So we curated the data sets to some extent and rebuilt all of the models. One of the most significant changes in ADMET Predictor 7.0 is we significantly extended the pKa model. So we've added about almost 20,000 high-quality experimental pKa values from a collaboration with Bayer Healthcare. And a few months ago, Robert presented a webinar on those updates, and I'll just kind of review those here. We added two new models. One is a PGP inhibition model, and the other is a model that predicts if a compound is likely to biodegrade. And I'll talk about both those models in more detail during the talk. We've also taken our CYP kinetic models and reconciled the three kinetic parameters, Km, Vmax, and clearance, via this equation. The clearance is equal to Vmax divided by the Km. CYP expression levels for different races can be specified by the user, for example, Japanese race or American. And then we've also added the ability to export GastroPlus enzyme table for the 5 major CYP isoforms and their Michaelis-Menten kinetic parameters. We've also incorporated soft decision boundaries in ADMET Predictor, and I'll demonstrate the two types of functions to give kind of a softening on the boundaries of the thresholds. Okay, this slide shows a couple of the atomic and molecular descriptor changes that were made for ADMET Predictor 7.0. We've updated the partial atomic charges in pi subsystems that are calculated by our customized Huckel molecular orbital theory. So, for example, a chlorine substituted on a phenyl group, those partial charges have been updated and are much better in ADMET Predictor 7.0. We've also incorporated two new descriptors. One is a 3D descriptor, the other is a 2D descriptor, but they're both around the geometric radius. So RADS 3D is a projected geometric radius of a molecule averaged over all orientations. Similarly, T_RADS is a 2D topological version of RADS 2D. So it just uses the 2D structure to compute this descriptor. Several changes have occurred in the user interface. The first one is that there's a new ionization profile plots for tracking individual ionization groups. So we've incorporated an average single proton acidity graph and an average site proton graph. And then for each one of these, we mark the PK50, which is a single proton midpoint for each one. And I'll talk about those in more detail during the main talk. When you output or save an SD file, there are several different workflows that can be saved. So for example, medicinal chemist, physical chemist, computational chemist, and cheminformaticist. And this came directly out of our collaboration with Bayer. We have the ability within the model editor to turn off or on entire modules associated with a certain module. So for example, with the toxicity module, you can just click a single button and that will turn off all of the toxicity modules rather than having to go and turn off each one individually. Calculations can now be paused or stopped with the escape key. So if you're in the middle of calculating a large grid of models, you can push the escape key and that will pause or pause the calculations. We've also added color to indicate the shifting protons in the tautomer display, and so I have a slide depicting this coloring that I'll show. And then finally, we've updated the images of the molecular structures shown in the ADMET Predictor. We've added several new command line options. The first one are these -W and -S for saving different type workflows that I discussed on a previous slide. There is a -G option now for activating gastro plus table exports, both the drug table, the acid-base table, and I assume the enzyme table also. And then we've added another option, -N, which allows you to select specific module models to output. And when you use this option, it eliminates output of the descriptor columns. And this was from a specific user that was computing a lot of these on the fly, and the files were getting very big. So we've added this option so that you can not export the descriptor values. We have a large number of changes in ADMET Modeler. One of the ones that's the most significant is the ability to quantitatively compute predictive confidence values. And I'll discuss this in a bit more detail and show an example of these new features. Along with this feature, you have the ability to make confidence analysis plots, which plots the uncertainty and the error rate across the ensembles, or across the network, excuse me. We've added a new algorithm for selecting the best model in ADMET Modeler. So if you've used ADMET Modeler, you know that typically you create maybe 50 different artificial neural network ensembles, and then you want to pick the one, the best one, and so we've all implemented a new algorithm for selecting that. And then finally, when you display things like the confusion matrix in a classification model, or an observed versus predicted graph for a regression model, we've added the ability to keep the plots up so that you can compare model plots side by side. And again, I'll show an example of that. Okay, so that was kind of an outline of the talk. Now I'll go into some more of the details that were changed in the program. So first we'll start with the predictive models. There's a great expansion of the PKA modeling training set. So with a collaboration with Bayer, we obtained over 20,000 experimental PKA values, and over here shows the split of the training and test pool, and then the composition of each from public and Bayer sources. So the training pool is now about 25,000 data points, 10,000 came from public sources, and almost 15,000 from the biopharma collaboration. For the internal test set, there's about 8,000 pKa values, about 3,500 from public sources, and 4,500 from biopharma. So this is a plot of the observed pKa's versus the predicted pKa's for both the training set and the test set. And as you can see, we get excellent statistics in both sets, particularly the root mean square error on the training set is 0.475. Similarly, for the test set, it's about 0.497. And then these are the various statistics for the internal test set over on the right. And by the way, the internal test set is never used to train the models, but we compare those results of the training and the test set. So once we created the models, we sent them over to Bayer Healthcare, and they helped validate the models. So they looked at 3 external test sets that were never made available to us. So these are truly external test sets. Now, the first one contained molecules that were fairly similar to what we had as measured by the Tanimoto similarity. So in this test set, approximately 98% of the compounds had a neighbor that was 0.8 or greater Tanimoto similarity to one that we used in the training set. And our training set is denoted by BTR. Test set 2 contained compounds with a very strong acid or strong base. For this set, the Tanimoto coefficient was above 0.8 for 60% of the molecules. So 40% of the molecules were dissimilar from anything that we had trained the model on. And then finally, test set 3 was the most dissimilar to the compounds we used to train. So only 45% of the compounds had a Tanimoto similarity of above 0.8. And these measurements were made after Bayer handed us the training set. So here are the results and comparing the AP 6.5 predictions to the AP 7.0 predictions for these 3 test sets. So test set 1 contained about 4,700 molecules, and as you can see, we decreased the root mean square error from 0.82 to 0.41 for this first test set. The second test set was about 8,900 compounds, and again, we reduced the root mean square error significantly. And then finally, on the largest test set, almost 13,000 compounds, again, we had significant improvement of the model compared to ADMET Predictor 6.5. So overall, we had very significant improvements in the root mean square error. And we've had other companies we've made this available and tested this, and they all got much improved results on this. So we're very proud of the work, especially that Robert did in creating these models and the accuracy of the models. So we have some new concepts that we've added to the program now. So the first one is the average single proton acidity, or ASPA, and it's an effective pKa over individual ionized groups averaged over all the microstates at a particular pH. So this will be a plot of the average ASPA versus pH, and it's just a measure of the acidity or basicity strength of a particular group as a function of the pH. The average site protonation is the the microstate average protonation state of individual ionizable groups. So here we'll have on the y-axis the fraction going from 0 to 1 of each one of the ionizable groups, and what fraction of it is protonated as a function of pH. And then finally, a new concept I think that Robert really introduced is the pK50, which is a single proton midpoint. This is the pH value at which the ASP curve equals 0.5. So this ionizable group is half protonated. And it's an estimate of the group's acidity or basicity in a multiprotic molecule, but after these effects have been, of the other groups have been averaged out. So this truly reflects the strength of that particular group. Okay, so this slide simply shows the average single proton acidity for our old friend cetirizine, which has 3 ionizable groups. The first is carboxylic acid group, and that's shown by this red curve here. So we have the average, or the single proton acidity, around just a little bit above 3 if we start here at 0 pH, and as we increase, we get to the pK50 for this acidic group that's just above 3 on the pH scale, and then the strength increases or goes up as the pH increases. Then if we look at the nitrogen that's kind of distal from these two phenyl groups, that's illustrated by this green curve. So it goes up very steeply at around 3, and then its pKa or its pK50 is around 7. The other group, the highlighted here kind of in the blue, reflected in the blue curve, is much less basic than the one that's distal to the two phenyl groups. This next slide shows an example of an average site protonation, or ASP, again shown for cetirizine here. And so on the y-axis we have the fraction ionized. So for an acid group, when you're at very low pH, it's fully protonated, and then as you increase the pH, it becomes less and less protonated. So before you even get to pH 7, this is completely deprotonated. For the less basic nitrogen that's closest to the phenyl group, that's shown by this blue curve, and you can see that this is only protonated when you get down below 4 and significantly protonated around 3. So this is the pK50. So if you're down at very low acidic conditions, low pH, then this would be protonated, whereas the one that's distal is protonated even at up to 50%, even at a pH of 8. So that's shown by this green curve here. Okay, so this kind of shows the overall state for cetirizine. And you may ask, why are we bothering with these ASP, ASPA, and pK50s? So this slide is kind of a reminder. On the left, we show the macro states for cetirizine. So these can be experimentally observed in the macroscopic pKa values. Now these arise from statistically averaging the microstates shown over here on the right of each. So each one of the functional groups contribute to the macrostate environment. So you're not really getting the full individual ionizable groups. Whereas for the pK50s, the ASP values, these are deconvoluted from the rest of the other environments. So you get a much more true state of the acidity or basicity of individual groups. And that's really what medicinal chemists are after, is how acidic is this carboxylic acid or this amine group. So here are the ASP values at pH 7.4. So for the carboxylic acid, 99.9% of it is deprotonated at pH 7.4. For this nitrogen in the pyrazine ring, 85% of this would be protonated at pH 7.4. The other nitrogen, only 1%. Then down at the bottom are the individual pK50 values of each one of these groups. And remember, these the other groups have been deconvoluted from this molecular environment. So the pK50 for the carboxylic acid group is 2.7, and for the other two nitrogens, they're 8.2 and 2.35, respectively. Okay, so another option here now, when you go into ADMET Predictor and you do file save as, we have new options for outputting an SD file. These are for medicinal, physical, computational chemist, and cheminformaticist. So for a medicinal chemistry format, it will so for an example, in cetirizine, it'll output just a single structure, but you'll get the pKa in the text fields of the two strongest acid and basic groups in the molecule. What is the predominant charge state? So for example, for cetirizine, it's zwitterionic, and then a complete list of all the pK50 values for the three ionizable groups, for example, in cetirizine. Physical chemist output contains all the microstates, so for cetirizine it'll be 8 total, and the parent macro pKa, the overall charge state, and its prevalence. For a computational chemist, it outputs the microstates at pH 7.4 and their formal charge. And then finally for the chem informaticist format output, it's the overall formal charge state and its prevalence at pH 7.4. So let me just bring up ADMET Predictor and show an example of a simple molecule that I made up. So we've already calculated properties for this particular molecule, and if you click on a gray cell, it brings up the pKa microstate form. So let's start down here at the bottom of this chart, and so we have three ionizable groups, the hydroxyl group and the two nitrogens of homopropyrazine in this case, and at pHs below 2.5 everything's protonated. As you increase the pH, one of the protons is going to come off of this group, and we predict here that it comes off of this nitrogen more prevalent than the other two microstates. And then going up further, in this row we have the formally neutral molecule, but it exists as a zwitterion, either with the hydroxyl always deprotonated and one of the other two nitrogens protonated. And then as you go up further in pH, you get the hydroxyl group deprotonated, and in fact all the ionizable groups. So our special charts are can be shown by clicking on the ionization-related graphs icon. So we can click on the circle to loop through various plots, and when you get to the fourth plot, this is the first one that shows the average single proton acidities for this molecule. So on the y-axis, again, we have the single proton acidity, and then the pH going across here. And across this, of course, this bar, or this vertical line, as you move it across, you can click on a particular spot, and it will show the average single proton acidity for each one of these ionizable groups. So let me just kind of highlight that. So both of the nitrogens in the homopropyrazine at pH 7.2 have somewhat similar average single proton acidities. If we click one more time on the circle, we get the site protonations. Again, in red, this red dot is where the pK50 value associated with the where half of the group is ionized. So again, we can move across the plot here. Okay, so that's just a simple example of the pK50 charts, etc. Go back to the presentation and continue on and discuss the two new models in ADMET Predictor. So the first one is a PGP inhibition model. In 6.5 we introduced a PGP substrate model, which is a classification model. The inhibition model is another classification model. P-glycoprotein is a membrane protein that pumps substances out of the cell. So if your molecule inhibits it, that can prevent molecules from being pumped out of the cell. So maybe some sort of toxicological effect from inhibition of this. So we started with a publication from JMed Chem that contained about 1,200 structures. We curated the data set and corrected about 4% of the data in the data set. Inhibitors are defined as having an IC50 of less than 15 micromolar, and that was about 620 compounds. Non-inhibitors had an IC50 of greater than 100 micromolar, and that's about an even number of close to 600 compounds. So the model predicts whether or not a compound will inhibit PGP. I see I cut off a little bit from the end here, but these are the overall statistics for the model for both the training and test sets. And as you can see, the concordance is above 90% for both of the training and for both the training and test set. Similarly, the specificity and sensitivity are both above 90%. So a very nice classification model. The other model we added was a biodegradation model called ToxBiodeg, and this is part of the toxicity module. And basically, there were some publications and some protocols that are out on the internet. So we combined two different protocols. One is the OECD or MIDI-1 protocol, that's an 28-day protocol, and the Japanese MIDI, which is a 14-day protocol. With both of these protocols, basically the experimental procedure is to collect sewer sludge from different water treatment plants and kind of combine those together and homogenize those. Then you take a certain weight of the chemical that you're wishing to test and isolate it with this sludge sample. And so the enzymes in the sludge will begin degrading the molecule and will consume oxygen. So you measure the oxygen consumption of this mixture and then compare it to your computed theoretical oxygen demand. And a compound was defined as readily biodegradable if the experimental oxygen demand was greater than or equal to 60% of the theoretical oxygen demand, indicating that the compound was being chewed up. Overall, the data set contained about 1,500 compounds, and this is the ratio in the training and test sets. For these statistics, we get above 80% for all of the statistics. So again, a quite nice model. Not quite as high as statistics as the PGP, but still very nice. In ADMET Predictor 6.5, we introduced models that would predict KM, Vmax, and clearance on the atomic level. And so these were represented in the ADMET Predictor spreadsheet. We now have related these predictions according to this formula. And so we reconcile these so that they'll all of these will, the predictions will all match this, both at the atomic and molecular level. And so this helps rein in somewhat of the extreme predictions we were seeing before in AP 6.5 for either Vmax or clearance. Now, in the real world, when you measure these kinetic parameters, it can sometimes be very difficult to measure either clearance or Vmax. And so typically what experiments will do is measure one or the other of these quantities and Km and then compute the other quantity from the other two in order to reconcile it. So we're doing a similar thing within ADMET Predictor. Okay, the boundary conditions for ADMET risks have been modified. So over on the left shows kind of a hard cutoff. So if we think of a rule, let's say of molecular weight, so your molecular weight, maybe the cutoff's 500, and as you increase the molecular weight, you have 0 penalty until you reach 500, let's say, and then everything above there gets a risk score of 1. Well, a lot of people were, thinking about this, and a compound that has a molecular weight of 501, maybe that shouldn't be penalized as a molecule that has a molecular weight of 600. So the way to do this is create a ramp function so that now as you approach the cutoff, the ADMET risk will slowly increase until you get to a certain number, and then it will just be the full. So it's kind of a fractional ADMET risk. Instead of either an integer 0 or 1, you can have values of 0.5 or 0.75 depending on where you have the cutoff. And I'll show an example of this in ADMET Predictor in a minute. Another type risk score might be an equivalent one. So let's say you want all your molecules to have a log P of 3, let's say, and you want to penalize molecules that have a log P of 2 in the same amount as if they have a log P of 4. So this can be done with this function over here on the right. So as you get towards the cutoff, it slowly increases until you're at the cutoff, and then decreases on the other side. So the way we've implemented this is simply to modify our filter dialog here, and instead of just having a single minimum value, we have a start value and an end value in ADMET Predictor 7.0. And so let me just bring up ADMET Predictor again and illustrate how we do this within the model editor. So we would go under the tools, under model editor, and then create a new ADMET risk. Now usually I bring in an old file, so I'm going to open the absorption rules here and then just simply remove each one of these rules here. Then I'm going to add a new rule and just give it a code of MW. So when I click OK, it'll appear down here at the bottom, and we haven't defined the rule yet, but we defined the code MW here. So then I'm going to go to our MW calculation. We have greater than for the operator, and I'm going to say start the ramp at 450, and once it gets to 550, then you fully penalize this. So I'll add that to the rule, and so now it adds MWT greater than 450. That's where it starts, and then in curly braces is 550, and where you would fully penalize that. So I'm going to save this as a new rule, simply just call it MW as a file, and then once I close this, I'm going to be prompted for if I want to add 2 columns, and yes I do. So one is going to be the actual risk score, and the other one will be the code. And also under the format, so with the old rules, things were integers. So I'm going to change the format down here so that when we look at this in the spreadsheet, it's actually a fraction or a decimal. And then add the code column here, and then append this as the last model. So these show up here. We'll save the model editor, and then we'll read in a random set of 250 drug molecules, calculate their properties, okay, and then these new risks will show up in the user models tab. So here we have the MW risk and the MW code, and let's sort that from high to low. So here we start seeing some ones with a value of 1, so these are some of the high molecular weights, and then as we scroll down we should see some fractional ones. And the best way to really look at this is to create a graph of the molecular weight versus the risk value. And so here you'll see it. The compounds with low molecular weight have a risk value of 0, and then as you get to 450 it starts to increase. We can click on a few of these points here, so the risk is about 0.44 for this molecule. And then of course, you know, these various risks can be added together to give an overall risk factor here. Okay, so now let's go back to the slides. So with our model editor, as I mentioned kind of in the introduction, we've added these options down here at the bottom to turn off or on an entire all the modules associated, or all the models associated with the particular module. So here's the physical, chemical, and biopharmaceutical. We can turn that off, or the other ones. So this is just a nice little feature to avoid having to click on individual models to turn off all the modules. For our tautomer display, we've now color-coded them to indicate the shifting hydrogen. So here kind of is the base structure where all the atoms colored in red, and this is for our alpyranol tautomers. So this simple one over here on the right just takes the pyrrosol portion of the bicyclic ring and has the hydrogen going from here over to this nitrogen. And so this coloring just allows you to see where the hydrogen has moved from the base structure over to the tautomer. And then, of course, some of them are two moves of the proton around here. So that's a very nice display and allows you to really quickly see what tautomers are possible in the molecules. Okay, so now moving on to the final section, ADMET Modeler. So we've introduced confidence analysis. So in ADMET Predictor 6.5, we did include confidence with models that we built here at Simulations Plus, and then we've simply automated this procedure and allowed it for users who define their own models to also include confidence estimates with their predictions. So typically our models contain 33 individual neural networks, and so the uncertainty is based upon the degree of concordance among these individual networks. So if you have a molecule where all the networks predicted it was positive, all 33 predicted it was positive, then you have more confidence in that prediction than a similar prediction that would say have only 25 out of the 33 models predicting a positive. What we've done as a further step is actually analyze the data coming out of the actual model. So on the left here is shown the error rate and uncertainty versus the tally of positive votes. And again, typically this range on the Y would go to 33 networks. So in red is the observed uncertainty and error rate at each one of the tally of positive votes. We fit this error or uncertainty to a beta binomial, and that's shown as the dashed line here. And then with this, you can also look at the predictive and error distribution, and that's shown here over on the right. And note that this axis is in a log scale. The black are the actual number of predictions, so at a tally of 0 positive votes, just over 100 predictions are made that contain 0 positive votes, and then the error rate is shown here in red. Now, as you get closer to this cutoff or threshold, you see points where there's a small number of predictions, but most of these predictions were actually incorrect, and that's what accounts for this high uncertainty. So around this graph is the uncertainty shown in those. Now, once you've created a model and then added it to the model editor and displayed its predictions, each one of the predictions gets a confidence value or estimate in parentheses. So if we look at this first model, or first molecule, the 1A3 predicts that it's not a substrate for UGT 1A3 with 80% confidence, whereas for 1A4 you have 98% confident in this no vote. So again, let me bring up ADMET Predictor and show an example of let's see, which one do I want here? I think this one. So this is a classification model, and I've simply read in old models, so this is a reload. I simply went to File, Reload, and reloaded this model run. So let's just pick an arbitrary model, again, you would get the confusion matrix here, and then by clicking on the button in the upper right, we have the CFA plot. So in red are the observed error rate and uncertainty for a particular tally of positive votes, and then in dashed black is the beta binomial fit to that. And then we can also display the predictions and error distributions. And again, this is a log scale. Most of the predictions either have 0 positive votes or 33, and that's kind of, you know, the most confidence you'll have are on the ends. And then as you go down here, we get more errors, and that's illustrated in this uncertainty plot over here. Okay. So now flipping back to the slides, so we have a new model selection tool within ADMET Modeler, and this is assessed by this Find Best Ensemble. So this was also in 6.5, but now when you click on this, you'll get a new dialog box indicating the new selection methods. We've added a dot product calculation and a border rank. You can also display the rank as calculated by these two methods. You can use your verify statistics also, and then you're able to include different metrics in this calculation. So on this next slide, I just want to show how the dot product is calculated in this example. So once you make a modeling run, you'll have values for the different metrics of sensitivity, specificity, and concordance of both the training and the test set. And the idea with the dot product is to simply multiply the values together and then add them up to compute a score. So the first step in the process is to normalize all the statistics between 0.5 and 1, and then the second step is to calculate the dot product and then identify the high scoring models. And the idea is basically the higher the sensitivity and specificity for the training and the test, that model is going to be better than another model that has lower sensitivity for the training and the test. With the board account, what we're doing is ranking each one of the different models based on statistics. So in this example, we have 3 different models, green, red, and blue, and we've computed the Uden value, Uden index for the test and the train, and then simply rank those in order of decreasing Uden values. So for the training set, the green model had the highest Uden, red second, and blue third, so these are the simple ranks. For the test, the blue was the best, green was second, and red was third. So that's illustrated over here as these numbers, and then you simply add those together, and then the one with the lowest overall count is the highest ranking. So these would be the best combination of train and test Uden values for these. So again, let me quickly pop into ADMET Predictor and show this for a regression equation. So when you build a new model, there's going to be defaults, and I think by default it'll be show the advanced settings. So if I don't have this clicked on and I simply click Find Best Ensemble, it will highlight the ensembles that are the best. If I click this on, then this dialog box comes on. I can select either dot product or border rank, and I can also display the scores. So I like to kind of display the scores, again, using the verify statistics. So this is a regression model, so I'm going to display the ranks, and I'm going to use root mean square error, the Spearman rank correlation coefficient, Q-squared, and slope as metrics to compute the dot product. We also have a checkbox for model complexity. If this is turned on, it will try and use models that are less complex. So with the ranking this checked on, this form comes up, so let me just increase that a little. So these are the numerical ranks of each one of the models. So it says a 10 input, 4-neuron has a score of 0.884. The second ranking model is 0.862. As you can see, these two top ones are kind of clearly ahead of the rest of the models. And so when it color codes these, it goes from green as the best, and then kind of a darker blue as the lower rank of the 10 models here. So we can simply click on this and look at this plot. Also within ADMET Predictor 7.0, we have this option to keep this open. So that allows us to click on another model, and then we can kind of compare these side by side, and again turn off different points in these, and kind of compare these directly to each other. And I think this one looks a little bit better than the other, than the model over here on the left. Okay, so now returning back to the slides and simply summarizing the talk. So we put a large amount of work into retraining every one of these predictive models. All our 140 predictive models have been newly trained for ADMET Predictor 7.0. We've significantly expanded the pKa data set. We've added 2 new models, PGP inhibition and biodegradability. We've reconciled the kinetic parameter predictions, added soft boundaries to ADMET risk, color-coded the shifting proton in the rototomer display, added new confidence estimates for the predictions, and confidence estimates to classification models, and then added a new selection tool in ADMET Modeler. And so I thank you for your time, and I think I'll throw it back to John.
Okay, thank you, Michael. Very nice job summarizing all of the new features in ADMET Predictor 7.0. I think now what we'll do is start the question-answer portion of today's webinar. Just as a reminder, you may either send your question using the questions pane on your control panel, or you may ask your question directly using the hand-raising icon. If you are using a telephone to listen to the call, please be sure to enter the unique audio PIN displayed when you join the call. When you enter your audio PIN, this will then enable us to unmute your line so that you can be heard. Now I'm going to ask Robert to act as the moderator with respect to any questions that might have been written in during the course of Michael's presentation.
Absolutely. We have 12 questions, now 13 questions. Let me start from the first one. Muhammad Jawad asked, can we get a recording of this webinar at the end? And the answer is yes, absolutely. I am recording this webinar. It will be posted on our website, and when it's ready, all participants will be notified by email. The other question by Venkataswara Pavuri. Is it possible to make absorption predictions using salt forms of compounds? It's yes and no. when compounds is in when salt is in water solution, it dissociates into its components. So what ADMET Predictor does, it can predict absorption of each component separately. And there is essentially the way how it works. There wouldn't be a quote unquote salt form absorption that would influence the absorption. Now, I know it does, but there is no currently any way to do it in ADMET Predictor. Another great question, can ADMET Predictor models be run on a Linux server and called up by other scripts to generate output files and analyze results, or it is only designed for Windows platform? So up to version 6.5, I would say Windows platform, but now we have a great news that in fact ADMET Predictor 7.0 will be able to run on Unix and Linux platforms. in its command line mode. There's no graphical user interface, but in its server version, as Gennady Poda asked, is ready to go. And in fact, at some customer sites, it is already running on Linux platforms. So if you're interested in Linux version, please inquire to us directly. Michael Crook asks, which descriptors have been used for the similarity? And I think this refers to our collaboration with Bayer Healthcare. I think Michael mentioned the external test sets set up by Bayer, and there are for those test sets, the distance to the training set has been determined by Tanimoto's similarity. And from what I know, the MACCS 166 fingerprints were used to calculate this Tanimoto score. Mario Lobel from Bayer, this is our collaborator in fact, asked the next question. Please comment on the format of the computational chemistry output STF and potential use applications. So because the picture is worth 1,000 words, I am going to actually show it. I hope everybody can see my slide. This comes from a webinar that we did back in October that was illustrating our new S+ PK model. And Mario put this slide together that illustrates how the computational chemist format can be used, and it's used by Bayer. In short, the format is used to prepare light libraries for high throughput docking applications. And the advantage of this format is that it shows all relevant protonation states of a given structure that are dominant at given pH. So in this example, you can see it's a tyrosine. It can exist as 3 dominant forms at pH 7.4. This is fully deprotonated form with overall charge state of -1, and 2 neutral forms which are Zwitter ionic. I hope that answers the question. The next comes from Gennady Poda. Have you tried the RAM function to be sigmoidal? This refers to our soft ADMET risk boundaries. Yes, we have implemented the simplest one, the linear RAM function, and of course there are many RAM functions possible. You know, there's really no compelling reason, at least we haven't found it yet, to use a sigmoidal function, which is more complicated and more CPU consuming compared to the linear form. As soon as we find advantages, we will implement it as an option. Mario asks the next question, has the new PK model improved the predictive performance of the retrained aqueous solubility model? So yes, it did, but only slightly. The RMSE improved in the 2nd decimal digit. And you may feel disappointed about it, but let me tell you that our ADMET modeler program does not overtrain models, period. It will stop upon reaching RMSE that is equivalent to the experimental quality of the data. So by experimental quality, I mean the variability of solubility measurements across different labs and performed by different scientists at different times. And we have assessed that this experimental quality of public solubility data is equivalent to about a half log unit. Thus, we have already reached that half a log unit in terms of root mean square error a long time ago. So the solubility model is not determined by the quality of descriptors, but the quality of the experimental data. and we have already reached that stage. So no further improvement is expected from changing descriptors, molecular descriptors. I think we already have optimal descriptors, optimal model, and the only improvement that one can get is to fit the training set with experimental data of higher quality. So I take this opportunity to invite anybody who would like to improve quality of their models that would be similar to improving quality of our PK predictions. Due to excellent collaboration with Bayer, we managed to improve the model greatly, especially its external productivity on industrial compounds. And I can only expect the same happening for things like solubility, log P, or any other quantity of interest. And Bob wanted to say something, please.
Yeah, what Robert said is exactly right for the overall statistics of the solubility models. That said, there are probably some individual particular compounds where the solubility predictions will have been improved. We haven't gone looking for those, though.
That's correct. Next question was asked by Gennady Poda again. How do you define the applicability domain in your confidence analysis? I thought that closeness to applicability domain would be a good measure of accuracy. Yes, we do use neural network ensembles as our modeling engine. And we do indeed measure the distance to applicability domain via the ensemble variance. An ensemble, as you know, is a collection of individual models, neural networks in this case, and how much they vary from each other is a good measure as a distance to the training set, I would say. And it does indeed, it is indeed used by our new confidence algorithm. And this is not a new thing. It has been published, and I think Gennady himself was involved in some of this work. So in fact, we do use it. Jed Zaretsky, yeah, go ahead.
Robert? Yeah, I guess, let's say your molecule is close to something, your arbitrary molecule is close to something that you predicted in your training set. So that would give you, close to the applicability domain. But what if your prediction's wrong? I mean, how does that affect the confidence analysis?
We have seen those cases, Michael, in fact, where the prediction was wrong and the confidence was high. So how could that be? And in many of these cases, when we went back to the original literature, it turned out that there was either a mistake or a disagreement between different experimental measurements. So you should also or always make room for the possibility that the experimental data itself may be wrong.
Right.
Okay. Another point is that there's considerable literature on using direct measures of distance to the applicability domain as it's traditionally defined and as we define it, which is how far it is away from the training set descriptors. And nobody has ever been able to get anything better than a very coarse correlation between any of those measures of distance and uncertainty. This methodology, as Robert said, is based in a way on applicability domain as assessed by the variance in the ensembles, because each ensemble is trained on a different subset of the data. But this is really quite different than anything you're going to find in the literature yet. We're working on a manuscript for submission right now. It's been described at a couple of public forums, but it's not published quite yet.
That's correct, Bob. Yes, you're right. Jed Zaretsky asks, is it possible to train new SIP site of metabolism prediction models using in-house data? If so, is the only requisite that the data is encoded in a file in the proper format? Unlike the models that are based on molecular descriptors, which are very easy to train, all it takes is just to load an input file in one of the formats recognized by ADMET Predictor, which is SDF SMILES or RDF and so on, and you can build a model right away. The site of metabolism model, as well as the pKa model, those models are special because they rely on atomic descriptors. So to answer the question briefly, yes, it is possible if you ask us to do that. An average customer that just has an ADMET Predictor and ADMET Polar right now is not able to build those models, at least not yet. Okay, having enough interest, we can actually start enabling features of building models based on atomic descriptors as well. Jed asks again, is it possible to build new models incorporating in-house metabolite data with ADMET Predictor space SIP metabolite data? So this is a different story, I think. I think Jet is asking about the kinetics, metabolism kinetics. Is that correct? No? I think this relates to the previous question then. The prediction of metabolites is directly tied to prediction of sites of metabolism. Actually, there's a synergy between two programs, between ADMET Predictor and our other program called MedChem Designer. The sites of metabolism predicted in ADMET Predictor can serve as inputs to MedChem Designer, which in turn generates metabolites. So I think these questions are directly tied to each other. Okay? Once you can predict sites, you can predict also metabolites. Hernand Joshi asks, can we calculate occupational exposure limits, OEL? Currently, there's no such model. Nevertheless, there is nothing standing in between using your own in-house data and building that model yourself or asking us to do that. We will look into it in terms of searching the literature and available public sources for this kind of data. If there's interest, and we'll be very happy to attach this model to our toxicity model.
Yeah, I think just looking at some of the questions that Hemant's asked, he might be interested in looking at Gastro Plus, which is another program created by Simulations Plus, and it seems like some of his questions, such as selecting excipients and looking at exposures, etc., might be able to be answered by Gastro Plus than ADMET Predictor.
That's correct. Fatima Bas is asking whether it's possible to apply an ADMET Predictor to natural products. The answer is yes. There's no difference between a natural product, providing the molecule is not too big. This actually is tightly connected to the next question. Can you analyze polymeric drugs? So ADMET Predictor has a limit on the size of a molecule that it can analyze, and the limit is arbitrary. It can be changed. I think it is right now 512 bonds. and no more than 20 ionizable groups. You may think, well, this is arbitrary, you can change it and so on, and you can increase it to 1,000 bonds or so on. Well, it's not that easy. This is because the training data for our models did not contain too many large molecules. So even if we can raise the limit to other number, higher number, it is likely that the large molecules will be outside of applicability domains of all our models. Having said that, nothing prevents a customer to ask for a special version of ADMET Predictor with higher limit, and if the customer has enough experimental data, build predictive models using that data that applies to large molecules. And in terms of polymeric drugs, I think there is another twist. I think polymers can be represented inside ADMET Predictor as monomers. The descriptors can be calculated for monomers and correlated with the experimental quantity of interest.
One warning about that.
Mm-hmm.
If you try to import an RD file, I think it's an RD file, that has a monomer definition in it, a polymer definition where it's the monomer with brackets and the repeating count, that will not be parsed properly by Predictor.
True. You're absolutely right. So with appropriate caveats, it can be done. Xiao Chang asks, is the hepatic clearance predictable assuming that only the 5 major CYPs are used? Yes, the answer is yes. If only the 5 major cytochromes in human, or our models are predicting metabolism in human, if these 5 major cytochromes play the role and all other enzymes are insignificant, then yes, it is possible to predict metabolic clearance.
There's a caveat to that I'd like to put in, if I may.
Mm-hmm, go ahead.
People have done a lot of studies. Most of the model, all but one of our clearance models, are based on recombinant CYPs. Those numbers tend to be higher than the clearance that you'll get in microsomes. However, it's also true that the numbers you get out of microsomes tend to underpredict what you see in the body. So if just adding up all the numbers coming out of the recombinant CYPs will tend to overestimate what you're going to see for total clearance in microsomes, but it'll probably do a decent job of estimating it for liver itself.
Thank you, Bob. Gennady Poda asks, is there a plan to add prediction of metabolically soft spots on small molecules, like, for example, Metasite does? Yes, we are already doing that. These are the metabolic site models that were already asked about by Jet Zaretsky. I think we implemented these in version 6 of the program. So it's been, these models have been present for some times already. Muhammad Jawad asks, once we have used ADMET Predictor descriptors during building QSAR model, I presume, will there be a need to validate the ADMET properties of molecules screened out through this QSAR model? The internal validation is done automatically by ADMET model. Unless you go through a trouble of turning off the selection of a test set, each model built by ADMET modeler is validated on a test set. Okay, this test set is held away from any of the training procedures, so you can call it an external validation. I can imagine that it's in a company setting, there will always be need for further validation. I would say using new data, new compounds that were synthesized after the model was built, and if it is found that the model no longer performs, okay? If it is found that the compounds are so new that they're just outside the applicability domain, then and that there is a sign to update the model with this new data. Next question by Hernan Joshi. Can ADMET Predictor help in selecting excipients for formulation? Yes, it can. It can predict quite a few important physical-chemical properties, such as water solubility and intestinal permeability and so on. So I can imagine that it is being used for this purpose. I think John DiBella can comment more on that because he has more experience with that. I also want to mention another software in our stable called DDD+, that is specifically designed to analyze formulations, including the complete analysis of formulation excipients. John?
Yeah, you kind of hit on it, Robert. I think that ADMET Predictor could be useful for predicting the excipient's physical-chemical properties, but it won't be able to predict the impact that that excipient would have on the API properties or on the formulation itself. And that's where you would then consider the transition over to DDD+ to be able to simulate the in vitro dissolution. And in that program, we have some models available to try and link the API and excipient interactions that might be at play.
That is correct. Thank you. Next question, Venkateswara Pavuluri. Can I get the evaluation copy of ADMET Predictor? Absolutely yes. There is no problem with doing that. I switched presenter window to Anu Sharma, who will hopefully display the slide with appropriate telephone numbers and email addresses where you can send your request. And you can also access our website. There's a special page for contacting us, and you can send an email through there as well. So while Anu is preparing the slide, let me ask the next question. Are there any prediction-based tools by Simulations Plus for salt selection for a given compound? Salt selection in terms of whether the compound, I presume, will be a good oral drug, correct? If yes, then we do. Absolutely. We have two programs, actually three programs. Along with ADMET Predictor, we have our flagship product called GastroPlus, which enables users to simulate gastrointestinal processes. It's not just absorption, but everything that is related to the interaction of an oral drug with a living organism. It all can be simulated. The DDD+ that I mentioned is designed specifically for studying different formulations in terms of dissolution. And I think the answer is resounding yes. We can do a very nice job for selecting appropriate salt, appropriate formulation in general. We also conduct studies if you want us to use our expertise to do that. We're very happy to accommodate that request as well. Gennady Poda asks about the statistical. I'm sure Gennady Poda actually made a comment. He completely agrees with the answer. Statistical instability of artificial neural networks and confidence in accuracy of predictions are not the same thing. He agrees with Bob's comment that was made earlier. So that's his message. There are some comments by Judge Zaretsky related to the questions that I already answered. Hernan Joshi asks, metabolism by other enzymes like esterases and hydrolase folic acid can be predicted. Currently not. We don't have those models yet. Again, there is no obstacle in creating models of interest from your own in-house data. Talk to us if you want to create a special model using atomic descriptors such as prediction of sites of metabolism. Any molecular model can be done essentially in minutes by anyone who has a license to the ADMET modeler. John, I think I will switch to you. Do you mind? And please show the slide with our contact information.
Okay, oh, go ahead.
Yeah, there's two more questions.
Oh, okay.
Can I get the copy of the program of simulations program for free? The answer is yes, if you are a qualifying reference site. If you're a qualifying academic reference site, then yes, it is possible to get a copy of the program for free, providing that you will use it only for scientific research purposes. Okay, so that excludes any work that relates to making a profit from our software, such as consulting. If you think that you qualified, please send us an application. Yes, Fatma Bas is answering that she does work in academic scientific research. So please submit an application to John. The email address is shown on the screen, and we'll consider you for the free copy of any of our programs. Siladitya Ray Choudhury asking us about the following. Has there been any thought given to building QSR models on the effect of excipients? This is along the lines of work done by Jean Revere on the effect of solvents on API permeability through skin. This will have a significant impact on drug and formulation development. In short, the ADMET Predictor does not really distinguish drug from excipient in terms of that it accepts any organic molecule that doesn't contain some exotic elements such as metals or silicon or selenium or things of this nature, and make predictions. So I think Ray is asking about more specific things like have there been studies, have there been models built that were based on specific studies where either tablets or capsules were administered to either people or animals and their effect was measured in terms of excipients. So again, we don't have any specific models of this nature. They can be built if there's enough interest. If anybody of you gentlemen has any other comment on that, I'll be glad to hear it. If not, then I will go to the actually, this was the last question. There are thank you notes and congratulations to Michael, which I also thank him for excellent presentation.
You're welcome.
So I guess we can wrap it up. If there are no questions, no comments, please take a look at the screen. There are addresses of contacts within our organization for all questions related to sales and marketing of ADMET Predictor and Metcon Studio. Please contact Ms. Anu Sharma. Here's the email address and phone numbers. The inquiries related to the cheminformatics studies, and in general we call them cheminformatics services. It's also an assistance in terms of building models and so on, data curation and so on. Please contact Michael Lawless, who gave you the presentation. And for questions related to GastroPlus and DDD Plus, and I presume also our new incoming product, new upcoming product called Membrane Plus, which will predict will simulate the apparent permeability measurement experiments. Please contact John DiBella. And as always, our website is open to all of you. There is a special form through which you can ask general questions at any time. Thank you very much for your attention. Thank you to all the staff members for helping putting together this seminar, especially to Michael Wallace for giving a flawless. He should be called Michael Flawless for giving a flawless presentation. And thank you again for your attention.